Well, hello everyone. Welcome to another CUIIC webinar. Today we're going to be talking about machine learning for depiction of underground infrastructure presented by Peter Srajer. I'll be your moderator today. My name is Marvin Lopez. I'm a senior sales executive at ProStar GeoCorp. So for the CUIIC webinars, CUIIC is the Canadian Underground Infrastructure Innovation Center. These are complimentary bi-weekly live webinars that are going to be presented September 15th through December 8th of this year. And for the full schedule, you can visit CUIIC.ca for more information. What is CUIIC? CUIIC is a cross-Canada hub for research and education in underground infrastructure located at the University of Alberta. CUIIC is a membership-based organization that involves stakeholders, including municipalities, contractors, owners, and others, to identify pressing issues facing the underground sector. CUIIC stakeholders represent all underground infrastructure domains, including water, wastewater, transportation, gas distribution, energy, power, and telecommunications. These sectors face similar challenges related to the construction and maintenance of underground infrastructure. CUIIC is a membership-based organization. Membership is open to manufacturers, suppliers, contractors, consultants, utility, municipalities, and nonprofit agencies. Once you become a member of CUIIC, you become an official research partner with the University of Alberta. You have access to all CUIIC Connect groups and forums. And if you'd like to learn more about becoming a member, visit cuiic.ca/membership. To introduce our presenter today, Peter Srajer from ProStar. He is the chief scientist at ProStar GeoCorp, charged with advancing the geospatial technology solutions. He has over 20 years of experience in research, development, and implementation of advanced geospatial technologies in a wide variety of fields and challenging locations. Peter holds a master's in geomatics engineering from the University of Calgary, as well as being a licensed land surveyor and a professional engineer. Thank you everyone for joining us today, and I will turn it over to Peter.
Wonderful. Thank you very much, Marvin. I appreciate the introduction. Okay. And also thank you to CUIIC for allowing these weekly, bi-weekly webinars. It's a great way for us to get some ideas and look at what else is new out there and to talk to other experts. So I definitely encourage anybody on the webinars now to look at all the other ones and to look at the ones that have been recorded before, because the amount of information we're getting is absolutely fascinating. So on to mine. I'm going to be doing a kind of a overview presentation of how a couple of use cases are done for machine learning in the subsurface utility engineering market. There's lots of different ways we can be using it. I'm going to kind of concentrate mainly on the initial prospect of when we go out there to look for underground utilities, and the final end where we look at how do we visualize these, how do we classify the underground utilities, and what we can use for making proper decisions on what we can do with all that data. Right now, one of the biggest challenges in many jurisdictions and in infrastructure project is that a lot of the underground utility data is quite poor. It's been there for 20, 30, some areas 50, 60, 100 years. And the documentation of that has been either lost, never done in the first place, or poorly maintained, so it's not really available. In the digital world, we always expect to be able to go to your computer, bring something up and see what it looks like. Fortunately, we're not there yet. The level of accuracy will vary. The data is often out of date, and if you have abandoned infrastructure, it's almost ignored in a lot of cases. So while it's never critical safety-wise to hit abandoned infrastructure properly decommissioned, it is could be damaging in other ways. We now have a lot of variety of tools where we can detect, identify and map underground utilities, especially in fairly high precision. But that's an expensive and very time-consuming proposition to send out a SU crew. Anytime you have to send out people into the field, you want to make sure that they have all the possible information they can possibly have, primarily for a safety-related area. if you know going out into the field that there's a gas line, 4-inch gas line, 6 feet below you, well, you're going to, shut down that excavator instead of just willy-nilly digging. You want to be very careful of that. So what we're looking at is using machine learning as a way to conglomerate a lot of this information that you may be sending out and try to get some, I guess, expert knowledge of what you can expect when you send out a field crew. It is very standard SUE practice and location service practice to consult all sorts of existing records from utilities, improvement plans, data from utilities, from the municipalities, as built, as designs, et cetera, including things like right-of-way records from your local governments. Now, when you're sending that out, that's great, but it's a lot of data. Another step is when you have possibly high-resolution aerial imagery, satellites, planes, UAVs, all the same thing. If a human being looks at, and as a trained human being who are looking for underground features, you can see a lot of things in the surface, like maintenance holes and valves and everything else, and vegetation differences that kind of give you an indication there might be something there. That's before you send out a survey crew to investigate what's out there. Before you send out your GPR units, your locator units, take a look at all this data and see what you can find. Issue there is you need somebody who's an expert to be able to initially look at that and tell you, this is probably here, take a look at this, look at this. Hard to get those experts nowadays, it really is. So what we're looking at is not getting rid of that expert, not by any stretch of the imagination, but have that expert impart their knowledge, into a machine learning algorithm. Say, okay, if we see this, that indicates this. If we see this, that indicates this. That way we have an ability to, leverage that knowledge, leverage that years of your experience to say, okay, what is out there? What can we do with it? So it's really this preliminary discovery, analysis process that we're trying to automate. Okay, so an analytical purpose. Why use machine learning? If you already have a human out there doing this, and if you had no shortage of humans able to do this, then maybe we don't need to do this because, initially machine learning is an expensive proposition. There's a lot of training of the data, understanding the data, cleaning the data. Cleaning the data is going to take half, if not more, of your time for a machine learning project. I know a lot of places don't like to tell you that, but it's an intensive process requiring expertise in that area. Humans are very, very good at what's called pattern recognition and inference. By that, I mean, if they see, a picture of a cat paw, well, we assume there's the rest of the cat attached to it. That's something that machine learning cannot do. It doesn't make that inference unless you tell it. So telling it is done by giving it rules or the algorithms to say, if you see this and this and this and this, that implies this. That's all machine learning is. The interesting thing about machine learning is it's nothing new. For those of us in the surveying end of things, there's something called least squares analysis. That is a variation of machine learning. So this was done by Frederick Gauss back in the 18th century. So we're riding on the shoulders of giants on this. So consider that. In use cases for, say, construction, a lot of the critical requirements are data accuracy, data currency, how well you can integrate that information, and the completeness of that information. Completeness is kind of the critical area. We can integrate all sorts of data as much as we can specific to that underground utility. Problem is, a lot of the utilities are from different entities, or they're siloed within the telecom, within the gas company. So whether we can build on that or not is another issue. Machine learning needs that kind of information and a lot of that information, the map bases, the standards, and all that has to be brought in. when I say data that we need to bring in, it is not just spatial data. It is not just, okay, here is a manhole and its accuracy is this, that, and everything else. Those are critical, especially the accuracy parts. But we also have to understand and put into the machine learning algorithms that this pipe has to connect to this pipe. Those are the rules we're getting. The key to integrating, live data, ensuring that all the geospatial systems, that model the data, you have to have a common standard. And there are standards that we're working towards, like the muddy data model. May also want to call that a data schema. And these are kind of based and following the accuracy standards of, ASCE 3822 and the 75-22. Those are US standards, but consider them to be kind of the base model of what we want to look at. So we want to take those standards and be able to apply or push them into the machine learning to understand, okay, if the accuracy is, at the meter level, well, that's one thing, that's great, but don't expect anything better than that. It's the old garbage in, garbage out. Machine learning does not make the data better. Unfortunately, it tends to mask a lot of issues if they come about. So what our goal is to basically train the machine to recognize a pattern. That's something humans are really good at. So we have to train the machine to do it. And we have to understand what the rules are. This is where expert opinions come in. People who know what they're doing out in the field, the engineers, the surveyors, designers in the office. This is not something that you can just throw data at and hope that it works. Garbage in, garbage out, like I said before. So the idea is we integrate our existing data, GIS data that we've had, LiDAR, 3D scanners, asset data from the municipality. Where do we expect things are going? Where does it make sense that they are going? And we push that into the machine learning system and you get a better view of what to expect in the field. The picture here on the right-hand side, the white pipe and the green pipe there, that is the correct connection for those pipes. From a human point of view, you look at that and you think that's wrong because that doesn't make sense. But in actual fact, that this comes from a city in Ontario, Hamilton, which in this case found out that a lot of their storm sewer pipes were cross-connected to the sanitary sewer pipes. The top one there is a storm sewer, the white. The bottom one is the sanitary sewer. As a human being looking at that, you would expect them to connect straight. It's just a natural perception. That is wrong. And that's what they found out. Whereas a machine would look at that and go, okay, that's one aspect, we've kind of expected to go straight, but a machine learning system also understands this is a stormwater pipe. This is a sewer pipe and they should connect to each other. Whereas a person out in the field that's, doing the work, the hard work of actually connecting these things, probably will look at that and just cross connect them straight. So the more information you have, the better decisions you can make on what's going on. Next page here, sorry. Okay. I'm going to go a little more into the details of the machine learning end of things and how processing and modeling and some of the kind of an overview of the models and what we're doing. For the most part, for underground utilities, we're kind of doing what's called a support vector machine. These are classified as supervised algorithms. What a supervised algorithm means is you are training data. You have a data set that the results or what they should be. And this is how you train the machine learning model to understand that if you give it a similar set of circumstances down the road, you expect this is the result. I'm glossing over a lot of the math because we have half an hour here, so we're not going to go on that. But really, artificial intelligence, machine learning, it's a very complex mathematical process, but the understanding is quite easy. If you give it enough data and give it good data, give it a goal. This is what we expect the results to be given this training data set. Eventually, it will figure out a relationship between the data and the results. It will fail hundreds of times while you're training it. That's what the computer's for. And then eventually it will give out, okay, given this set of data, this is the result that I have. This is the mathematical model. You give it the entire data set, realize it doesn't quite work, readjust it, put it back in, try again, try again, try again. That's all it is. It is a cumbersome process, but in the end, what you're trying to do is get as accurate of a data model as you possibly can. Nothing is 100%. It's just not going to work that way in the field and in real world. There's really two types of models that we're looking here. For the most part, we do what's called predictive modeling, which is, like I said, take and identify relationships between the input variables, what you have, things like a 6-inch pipe is generally only designed for water, gas, sewer, such and such, such and such, or a long 32-inch pipe. Well, that's probably a big mainline gas line. Things like the expert opinions on the input of what it should be. This allows you to gain some insight on those data points that are coming in, and they allow them to cluster them. What you see on the screen there, the red, blue, and yellow, that's not geospatial positioning. That is a data model, for example, saying, okay, if this is the size of the pipe, this is generally what I consider the type of pipe to be. If this is the size of the pipe, then this is generally the material it's made of, things like that. Cluster analysis, that's what it is. Your output is not always very clear response. It's basically a dependent variable, but what it's revealing is common traits that, given different variables, this is the commonality they have between them, and this is how we can model them and tell you what they are. The other model we generally tend to use is called a forecast model. That's more likely done for, failure analysis. You get a lot of historical data. This pipe has been in the ground for X number of years. It's made out of Y. Interior diameter is Z. It generally is in this type of geotechnical environment. We'll make predictions on it. This will fail within the next 8 to 10 months. That's the kind of thing we do for forecasting model. Extremely, extremely valuable, but a slightly different idea of what we're doing. This is called classification or regression. Again, this is, if you look at how least squares works, or any of the various techniques like regression techniques, you're basically trying to find a dependent variable and predict the output. This is a lot of cases where IoT devices are used. Devices that are monitoring one or two single variables, temperature, time, pressure, et cetera, et cetera. These are now sent up to a central station. All this data is conglomerated, and out of the machine learning algorithm pops up, take a look at this piece here, because based on historical data, we expect this to fail. Now, I kind of glossed over the different types of data, because there's so many data points that you could possibly have that it really is difficult to explain. But since I'm a geomatics engineer, I'm going to pay special attention to spatial data. Spatial data is a kind of the poor child of the machine learning area, because it is difficult to put in properly. The reason is most data sets that you put in, features, if you want to call them that in the machine learning world, are, or you try to be as independent from each other as possible. That means there's no little or no overlap between the data. For example, the size of a pipe and the material are independent variables. One does not predicate the other. For the most part, there is overlap, of course. So you can basically look at them independently. One of the ideas behind machine learning is you also do what's called dimensionality reduction. That is, try to remove variables that say the same thing, okay, as much as you can. Problem is, with geospatial data, you cannot do that. You'll have an X, Y, and hopefully a Z, not necessarily, but those are not, they're independent, which means you have to have them, but unfortunately, you can't put them together as well as you think. Yes, there is an idea of, okay, instead of having X, Y, Z, let's say the distance from the feature you're looking at. That works fine, but that distance has to be recalculated and changed each time you're looking at something. So, spatial data is a tough thing to work with in machine learning. It's basically treated very differently. And in fact, XY data, horizontal data, is treated differently from Z data. Example of that is if you're putting a pipe in through an area, you need the Z value because you don't want to suddenly drop off a cliff. Whereas that XY won't tell you that. It'll say, yeah, that's fine, you can go that way. But you have to have a Z to be able to tell you, yeah, no, you can't go that way, or you have to go around this stream, for example, because of regulatory requirements. So there's lots of issues we have to look at there, not just a simple, okay, can we use this or how is it used? Geospatial is kind of nasty that way. So, yeah. Kind of the last idea on how we do data modeling, because it's kind of have to have an understanding of what we're doing here. There are really, for subsurface utility engineering, there are two ways of doing it. One, where we're doing straight machine learning is basically having a person or an expert in there constantly saying, okay, if this pipe is this is what it's made out of, this is what it can do, et cetera, et cetera. This is something that's always done at the beginning. You have the expert in there to be able to understand and give ideas to the machine learning algorithms to say, this is what it is. This is your input. Yes, based on these features and values, runs through the machine learning. This is your output. Yes, this is a car. Deep learning is where we're trying to push a little farther into it. We still have all the intelligence that we've learned from the previous stage of machine learning, but it's starting to learn on its own. I'm not considering calling this, artificial intelligence. It is not. We are, decades away from true artificial intelligence, if that at all. But it allows us to, use the learnings we've done from machine learning, put into the deep learning algorithms and feature abstraction. There are errors in it, especially in field operations. So we still need, there is no replacing, expert opinions or expertise in the field. That's not going to happen. What we do a lot of is also what's called narrow machine learning. We're not taking every single possible piece of data to try to derive some kind of prediction. In a lot of cases, what we do is image classification. If you go to the internet and bring up ideas on image classification, a lot of them have to do with facial recognition. That's a big area. But those same algorithms apply to underground utilities. Disturbance features on the ground in the vegetation. Looking and seeing, okay, that's a manhole. Okay, something has to be attached to that. Hopefully, things like that. So the idea is we're still using algorithms that have been developed for other purposes, but we are now training them for our own purposes. To give you an idea of one example of where this deep learning has worked for the most part, and why it doesn't is that NVIDIA, video card fame here, is very heavily into a lot of deep learning algorithms, especially for image classification. Being a graphics card company, that makes sense. They basically used multi-band spectral imagery, everything from UV to far infrared imagery, and they were trying to identify properties of a road surface from those images, whether it's asphalt, gravel, packed earth, and they're using very sophisticated algorithms to get this. Their training data came from in the Las Vegas area. And what they did and they found is that the results were amazing for the Las Vegas area. Once they've actually let it loose on the whole city, they could figure this out. But unfortunately, they found that they did 4 other cities around the world, did a very poor representation of it. So it actually didn't even work for the most case. And this is a company that had access to, incredible, high performance GPU assets and using, Amazon Web Services in our own cloud. So to get back to my point here, the idea is you cannot just train this on one specific area unless you want only for that one specific area. You need to be able to have sufficient amount of data and a sufficient variation of data to be able to understand and put into these algorithms. If your focus is very narrow, your results are going to be very narrow. And that's something that you have to look at. The idea is, unfortunately, in the subsurface market right now, we don't have a lot of data. What we need to do is collect the data starting now. If you have this in a digital format, then eventually you'll be able to have enough data to be able to do prediction modeling. Having all this data painted on the ground or a paper map drawing somewhere doesn't help as much as you think. This has to be digital data. This has to be able to be understood and be able to put into some kind of mathematical algorithm, or have an expert come along and say, this is what I expect these things to be. So the idea is we need data. We have to stop throwing away the data and collect the data and understand what it is. And additionally, when we have that data, we just can't say, okay, from point A to point B, there is a pipe. That doesn't help. I want, what type of pipe is it? What's its tensile strength? What flows through it? Wall thickness, how far it is below the ground at that point in time. All that information is critical and required. The more data you have and the more features you have, the better your model is going to be. So in the end, resulting, once we have all this data, we can start doing classification. We're not going to go out in the field and dig up the entire pipeline. We do potholes every 100 meters, 50 meters, whatever house you have there for regulatory purposes. But for proper visualization, we need to be able to have a continuous data set. And that's where a lot of the classification for machine learning comes from, is we can look at that and say, okay, we have 4 pipes in the ground, various depths. We expect them to be linear from this point to this point. I didn't say straight, I said linear, and that's a big difference here. And that's something machine learning will have to understand. It's not point to point, it's a continuous system. And that is where we looked at for the, support vector machines, which is a supervised machine learning algorithm. We are trying to be able to not just have point-to-point data, but a continuous network, where the valves are, where the manholes are, where the connectors are. So that is what we're trying to do with classification, putting all that data together and figure out what it is. Once you have classified everything like that, you can do what's called modeling. Modeling at this point in time, the machine learning will do a lot of it, but this is, at this point in time, very much a human expert-centric operation. It will tell you, machine learning will tell you, okay, this is where I expect things are connecting based on the information you've given me before, but you still need the expert to go in there and say, yeah, that makes sense. Are we 100% accurate? Absolutely not. Never going to happen. So what we do this analytics for is trying to improve the accuracy of the locating system, prioritizing and taking a look at where there might be problems, finding solutions. If you use predictive modeling, you can say, okay, do a risk analysis to say, okay, we expect there to be a problem here based on these conditions. Instead of being a reactive system where when something goes wrong, we go out and fix it. How about we basically say, okay, you know what? While it hasn't failed yet, the machine learning has told me, and I concur that this needs to be replaced. Let's replace it now. I'm pretty sure no utility, no engineering firm, no local government, or any government for that, wants to be on the front page of their local paper saying, we forgot to replace this because we didn't think it was a problem. That's never going to fly. So this is a way to say we did our due diligence. Yes, it'll cost possibly more because we don't wait till something fails. But first of all, safety of life issue is critical. I'm pretty sure one death is worth tens of millions of dollars in lost productivity, revenue, PR, everything else on it. So avoid that at all costs. Analytics basically will allow you to identify higher risk areas for given outage. And then you take other integrated data, from the GIS system, LiDAR, 3D scanning, asset data. You can use that to present to the engineers or designers and say, this is what we feel is a problem. So all these new advancements really allow you to visualize. And when I visualize, I don't mean just looking at the pretty picture like you see there in the bottom. That is a model of gas and electrical lines in a substation there. Visualize also means to look at and say, we may have a problem here, here, and here. This could come up in a spreadsheet. That's fine. That's still visualization. By visualization, I mean giving you information to make a decision. We have to do this, or yes, we want to put a new pipe in here and we have to reroute it around something. How do we do that? Can we push it into this, utility corridor? No, that looks like it's full. We're going to have to go around it. Oh, we need to put a pipe, from point A to point B. Oh, by the way, there's a large hill in the middle, or there is a river that you're not allowed to drill under. How do we do this? These little things come up with machine learning to say, look at this, look at this, look at this. These are the potential pitfalls you're going to have. It does not resolve those problems, but it tells you what to look out for. It is the expert in the field that has to deal with this information. That's where the decision-making piece comes in. We're not taking the person out of it. That's never going to work. The expert opinion, we use the expert to create the data to put in the machine learning took that information and based on that expert opinion gave its opinion, but then the expert has to basically go and say, okay, I see where that information came from. This is what I have to do. So this is what the whole design question improve, because the machine learning spits out an answer. You go, well, that doesn't make a lot of sense. So yes, now we do this differently. Let's improve the model. Push it back into the design, make sure the question is correctly. What are we asking for? And enhance the system. The enhanced system I put at the end because this is what we do at the end. Say, how do we make better decisions on this? If you spend time collecting enough data that is proven to be accurate, you have some kind of idea of the metadata, the pedigree of it, then you can feel confident in using that data. The machine learning is just there to make it easier. The time you spend processing the data, machine learning, if you've already processed it once, and you had the data, you save a lot of time if you don't have to do it again because you lost the data. Always consider that you want to avoid sending field crews out over and over and over again. And if you do send them out, make sure they have the proper time and understanding. So you spend the time to store, maintain, and update the data you have for your areas of where you're working. The visualization comes in, and this is, again, like I said, visualization is not just a pretty picture. It also means, the understanding of what that data means. How accurate is this? The problem with most people is when they look at a picture, they assume that it's spatially correct and it is exactly where it shows, the written in stone idea. It is not. We have to be able to look at it and say, yes, according to this 4-inch water line is here, but the machine learning is telling me the accuracy of the prediction on this is plus and minus 10 inches. That's poor data, but that's what it is. So it is that understanding, the visualization of not just the I guess, the things in the ground, but how accurate they are and how confident you have to be in those. This is the, an ideal way to be able to basically improve safety in the field, most critical thing, but also, make it much more efficient in the field. If you have all that information, then you don't have to do it again and again and again. And every time you do it again, there is a question of how accurate did you do it? So that really is, my understanding of, where we need to go with a lot of this stuff is that given the proper amount of information, collect it once, store it, and continue to use it and understand it. You get more data, great. Put that into the model, improve the model, and work on from there.
That's fantastic. Peter, thank you so much for all that. Anyone who is still on here with us, we're going to just go quickly to a Q&A section, but if you have any questions for Peter, here's his information. You can contact him through ProStar, and if you have any follow-up questions, just feel free to send him an email. I'd also like to thank CUIIC. This is going to be the next schedule of the webinar series that are going to be coming up. Next up, it looks like we have legal discussions, risk associated with underground construction on October 27th. So make sure to sign up and tune in for that. And we're going to open the floor for some questions. We do have a couple questions here in the QA. If you have any other questions, feel free to drop them into the QA chat and we will answer them here quickly. Peter, can you see the QA chat? Okay. I'll read out the question real quick. Okay. So the first question is, can AI be used to identify possible congestion areas or areas of high density for underground utilities where more attention/care is needed, for instance, conducting maintenance operations on new installations?
I don't know if you need AI to identify congestion areas. Okay, that is a geospatial idea, but it's a great question. Yes, you can. AI, given the proper geospatial coordinates attached to it, and also an understanding of how accurate the positioning is, because this is a positioning problem, will tell you, yes, you have a greater density of, pipes in this one area, and maybe you should try to avoid that area next time. There comes to a point where you can no longer safely put more features in there, or regulatory wise, you may be prevented from, co-locating, sewer lines and storm sewer lines too close together, like Hamilton found out. So yes, you can. I'm not sure if that's an entirely an AI system, but sure, let's go with that. Okay.
Thank you, Peter.
Hopefully I answered that. If not, go ahead.
So the next question is, what can/should be put into place across the industry to encourage stakeholders to provide input data to better develop AI systems for underground infrastructure applications?
No, that is a great question. Thank you to whomever put that in there. What needs to put in place is almost regulatory. This is not something that can be done by a locating company or the engineering design firm. This is a regulatory issue. They're the ones that can tell, your gas company, your fiber optic company, saying, you know what, you need to be able to tell us where your pipes are located, what kind of accuracy we have expectations of, and what is in there. There's an issue of security here, unfortunately, and understandable, absolutely understandable. So where this information resides and who has access to it is an entirely different ball of wax here. So I'm not going to go into that. I'm not an expert enough in the legal area for that, but this is a regulatory issue. If you want to push that, say, okay, you need to be able to demonstrate cost savings or safety on this. Say, okay, if you have a database available to properly vetted individuals that shows where your infrastructure is, then the chance of them hitting that or disturbing that is, drops by 90% per se. That will save you X million dollars. It's hard numbers that have to be brought up and say, this is what it's going to cost you if we hit. Mm-hmm. If you tell us where it is, then that goes down. Put it that way.
Thank you. It looks like we have just a couple more questions here. This last question, I think we've already touched base on this, but just to be sure we're covering everyone. Do most cities have a database imaging for infrastructure services in 3D? If so, when doing excavation, do we need locators if we have the database?
Okay. First part of the question, cities do have a database. How full and how complete it is, that is highly dependent on the city. You know, if you got a smaller city municipality that's been around for 100, 150 years, you know, probably not. They have very limited funding for it and budget for it, and perfectly fine, versus, you know, a large main city that probably has a dedicated system for this. But even then, I mean, I'm not sure if anybody's seen excavations done in New York City, where you look at the street and there is literally dozens and dozens of, you know, pipes and conduits underneath the street, and there's no way they actually know where that is. So the problem is, yes, they have a database most times, but it's not complete. And it probably does not have enough information in there to say what it is. And there's probably historical data they probably don't have in there. So do you need it, do excavation? Yes. You still need the locators to go out there. The idea is, though, is that going forward, you have better and more information every time, you know, a locator has to go out. So that the locator goes out week one, locates all the information, it's accurate, it has, you know, proper pedigree and precision on it, you know, and then the next time, you know, the engineering company comes in and says, okay, we haven't had any change since that point in time, so we can be a little more flexible on where we, you know, the data. It doesn't mean you can't use a locator. I mean, you still have to have that liability until we have a full and complete data set.
Absolutely. This next part is two questions from one individual.
Okay.
We do have they're asking for real world projects. Unfortunately, we don't have time to show any real world projects in this, but
No.
if you'd like, you know, get in touch with us and we can discuss otherwise.
Yeah.
However, they have a second follow-up here, and it says they agree that getting the data is very difficult. However, we need that data to move forward. Based on your experience, where is the best place to get the data, or what is the best starting point?
Best starting point, and, you know, I said this up there as well, is to start at the regulatory agency. Government agencies have the power to compel somebody to say, okay, you know what, you have to give us this data. You know, going forward, if you want to work in our right of way, you know, this is what Colorado DOT did. If you want to work in our right of way, you need to be able to give us digital information. There's your starting point. Starting point is always data, accurate data. If you don't have that, we're not going anywhere. And unfortunately, right now, you need the regulatory agencies and the large utility companies to say, okay, we need to be able to not only collect this data, but give this data or have people access this data if they need it for this specific purpose. Again, I'm not going to get into the regulatory body, legal liability type thing. There are lawyers that are far more capable of doing that than I am. Okay.
And then the very last question, is there a standardized platform, say across Canada, for companies to submit such information?
Well, sort of. I mean, each province has, you know, in the US, we call it an 811 system, you know, a call before you dig and things like that. But there is no standardized platform. It's very siloed. You know, most utility companies have that information within their GIS, whatever it happens to be, or within their CAD environment. There are a couple of groups, you know, CUIIC, QR, and in the British model, they've actually started building a national infrastructure database. We're in the infancy here. We are looking at how the British model is, and they are basically have a regulatory oversight to say, anybody, you know, digging into the ground, you need to give us your data. So not yet, we're working on it. That's all I can say on that.
Well, it doesn't look like we have any other questions. So once again, I'd like to thank CUIIC for putting on this webinar series. Make sure to check out the upcoming webinar on October 27th. I'd like to thank Peter for giving the presentation today, and everyone for attending. We appreciate your time, and we appreciate you being a part of this kickoff webinar series.
Thank you very much.
Thank you, everyone. Hope you have a wonderful day. If you have any questions, feel free to reach out to CUIIC for getting in touch with Peter and I. Thank you so much. Have a wonderful day.